we will continue on the digital interfacing. Last time we have covered the serial peripheral interface, the SPI bus, and today I'll cover another more very common bus that is used for interfacing digital sensors called the I2C or I2C bus. And before that, I'll try to recapitulate a little bit on the SPI bus, and then I'll move on to the other part, right? And if we finish it a little bit early, I'll wrap up the class, because let's not start with something completely new. If you have doubts, you can ask me. You can spend the rest of the time on that. Okay. So this is the same picture. Just to recap these things in your mind, we were talking about two types of sensors. One is the analog sensor that was going to the microcontroller via an ADC to convert the analog samples to digital form. And we spent a lot of time in understanding quantization and from a program the ADC and so on. Right? And then we started with digital sensor and that are capable of sending data through the serial interface. And in particular, we looked at one example that, like the keyboard that was sending data through the serial interface, and then specific protocols like the SPI, which we covered in the last class, right? And other common interface that also includes something called the I2C interface, or there is another protocol called UART or USART. So that is pretty common to what we have done with the keyboards. I won't cover too much details about that, but I would share you some pointers so that you can read it up on your own. Okay. So I'll try to give a like follow up on whatever happened in the last class. So in the SPI case, the communication was done by data transfer in between two shift registers, right? So the shift register 1 was residing inside the master, and the slave device had another shift register. And if the data was being transported from the master to the slave, which is called master out, slave in. So this is M out and slave in, right? This is one option. And the other option is that the data could also be transported from the sensor or the slave device to the master or the microcontroller through the other way around, the other direction, right? So this is known as the master in and slave out. So the data is originally coming out of the slave. And the clock control was in the hands of the master device. So the microcontroller is actually generating the clock, and that clock was distributed among the sensors. Okay. So all the slave devices that would be there in the system talking to the microcontroller, they would be fed the clock. And a particular sensor or a SPI device or like SPI peripheral could be activated or deactivated based on the chip select pin. So this is called chip select. There are many terminologies for the same pin. Sometimes they call it slave select, right? Sometimes it is also called CE or chip enable. So this is the pin that is going to select a particular peripheral device or a particular sensor. So you will turn on one of the sensors and then give it the clock, and then try to send data to that device or read data out from the device. So this was all about the SPI interface, what are the associated pins and so on. And as we know, all of these hardware peripherals have some associated set of registers, so that we can write software to control these devices, right, or control these peripherals, right? So in a microcontroller, as we have already seen in many cases earlier, there is always a set of associated registers, right? So these registers form basically the boundary in between your software and hardware. So if you write something to these registers using a software, something in hardware is going to happen. So this is basically the boundary, right? So like other peripherals, SPI registers are, there's only 3 registers. We have the data register that is going to be used for loading the data and reading data. either coming from the remote device or a sensor, or if I want to communicate some data to the sensor, if you want to send some data to the sensor, that's where the data register comes in. And to do the entire control of this scheme, to implement this different features inside the SPI register, SPI subsystem, we have these two registers called the control register, which has most of the functionalities here, and the status register, where we mostly used the interrupt flag, the SPIF, and the speed doubler as a part of the prescaler, right? So in the control register, the last 2 bits was being used as the prescaler, along with this one, the data rate doubler. So it is either 1 or 0, depending on that, whatever value is here in the last 2 bits could be multiplied by 2, right? And then we had the clock polarity and clock phase. We could configure the particular device as a master device or not, then it becomes a slave device. And then we had the regular SP, peripheral enabler or the interrupt enable. So this kind of bits were being used in these registers. Okay, so like you have to follow the general strategy, right? Whenever you want to learn about a certain peripheral or a certain functionality in the microcontroller, maybe some of them I will teach, but there will be many features that I might not be able to teach, right? Because of the brief amount of time we are able to dedicate to this particular portion. So even if you want to learn something, let's say you want to look at a different microcontroller and want to learn about a certain peripheral, so this is the way you should proceed, where whenever you look at the data sheet, you first have to know what is your hardware software boundary, like what are the different features the peripheral has, and what are the avenues in order to access those features, right? And those features have to be directly manipulated using some registers will be there, some configurations will be there, right? So that is how you write the driver, right? The bare metal program that you write or the driver for the peripheral has to be implemented using those set of registers, right? So that is why understanding these things very well is kind of important, and particularly if you want to write some efficient code, right, which is pretty much adapted to the features that you have on a particular microcontroller. Sometimes the concepts that I am teaching could be available right across different microcontrollers, but there could be certain nuances that you might have extra features in a certain microcontroller that you should be aware of from the data sheet. Maybe the way it could have a power saving mode, right, or there could be a certain high resolution mode that could be activated. So there could be extra things that a given microcontroller vendor implements. So you also discussed about the application flow, how the abstraction was added step by step, right from the bare metal. Then there is an SPI library on top of that, and then there could be a sensor specific library once you talk about a certain sensor, which uses the SPI bus to talk to the microcontroller, and then on the top you have your application. So this sensor library, mind it, last time I did not make it very clear. It's not just a function call to the SPI library, right? But there are certain things that the sensor library has, some information. So what are those information? Information is regarding information about sensor registers, right? So this is agnostic of the SPI bus, right? So there could be lots of different configurations that could be available. So the way I have written, let's say here, my sense.config is equal to config. So this config could be a list of different configurations, and those configurations has to be written to certain registers, right? A certain register could turn on a certain feature or turn off a certain feature. You want to decrease the resolution, increase the resolution of the ADC inside it. So in this way, those addresses, right, because that sensor manual will specify some addresses, and those addresses need to be actually programmed. Those registers need to be programmed. So that information is there in the implementation of that sensor library, right? And sometimes you want to avoid that and you want to quickly program the particular sensor. That's why they will give you a very nice interface where you can have a API called, let's say, like read the data, right? The way I have written it here. But just to read data, you need to initialize certain things inside, certain regular things inside the sensor. For that, you need to actually consult the data sheet of that particular sensor, right? Once you do that, then only you can read the data correctly from there, right? And the thing that the underlying communication protocol here is just SPI, and that does not mean that you can always communicate data, but the sensor has to make sense out of it, right? If you send a certain query to the sensor needs to understand what you are asking for, right? So for implementing that, you also need to consult that particular sensor library. Okay. So next, I'm going to talk about the inter-integrated circuit interface, or the I2C interface. This is pretty common, mostly for doing low data rate communication of the sensors with the microcontroller. Was originally developed by Philips Semiconductors, now called NXP. And I forgot to mention, the SPI was originally developed by Motorola. Okay, so different vendors actually created all this communication protocols for their own devices they were manufacturing. For example, Philips they were manufacturing television sets, right? And they wanted to use some protocols for communication of different components on the television circuit, right? So, and then later these things evolved, and as I mentioned earlier, that different hardware vendors who were actually manufacturing this CPUs, microprocessors, and all, they sort of adopted some of these common protocols. And then because of that, many vendors who are manufacturing sensors are bound to follow these protocols. And of course, there are pros and cons across different protocols in terms of power consumption, complexity of the circuit, how many pins you require, and so on. Right? For example, in case of SPI, we actually had 4 pins for the MO, SI, MISO. Then we had the clock, we had the chip select, and then there were additionally the VCC as well as the ground. So actually, there are 6 pins that are required to interface for this interfacing. So in case of I2C, this is ideal for attaching low speed peripherals to a embedded device for a reliable communication over a short distance. Okay, and the protocol allows the system designers to interconnect up to 128 different devices. So there is an addressing scheme where every slave device can be assigned, or they have possess a 7-bit address using only 2 bidirectional bus lines, one for the clock and the other one for the data. So in the bottom, you see that there is a single clock line and there is a data line, and the master basically shares the data path with all the slaves as well as the clock, right? And all the slave devices have some pre-configured address, right? Try to compare this thing for SPI. In case of SPI, we did not have anything called in-band addressing, right? There was no concept of address within it, right? So all the master was trying to do, try to keep a record of the devices that are there in the system, and based on that, it was trying to do some chip select, right? Which peripheral to select. However, in this case, it is not required. Every slave possesses a certain address, and that address could be either explored. You can do a search which particular set of slaves are present in the system. You can simply do an iteration from address 1 to address 128 and then try to see whoever responds, right? That's something very similar to a port scanning.
Excuse me, sir.
Yeah.
So these slave devices are, these addresses are programmable or fixed?
It is normally assigned to the vendor. So there is no restriction on that, for example, if you have your own slave device, you can program that, right? But normally this is standardized, right? Given a particular vendor, a particular device has a fixed address. That's how it is assigned or leased by this I2C group. But if you are like for your experimentation, suppose you want to configure an Arduino or some other microcontroller as a slave device, you can configure your own address, whatever you want. Okay, and there are certain reserved addresses. One example is all zeros, is called general call, that is normally reserved, but rest you can configure it yourself. But if you are buying a ready-made sensor from the market for a given company, a given kind of sensor, that will have a fixed address. Okay, and so yeah, the total number of devices here is restricted. Here it will go to as high as 128, and these kind of numbers are sort of important. Let's say you are looking at automotive applications where you do have a lot of sensors, right? So in that case, there will be a huge bus that is shared by all sorts of sensors, right? Obstacle avoidance, this ADAS kind of sensors, LiDARs, and so on, right? It's an advanced kind of an automotive system. Okay. And there are these 4 things we need to keep in mind. So the master is the device that initiates and terminates a transmission, right? So and it also generates the clock. Right? That was similar in the case of the SPI protocol. Also, the master is responsible for generating the clock, and the device is basically the slave device is addressed by a master. So the slave device is going to be called, the address is going to be requested by the master, and the slave is going to respond to that. And it could be either be a transmitter or receiver. It doesn't matter whether it is the master or the slave. They can do transmission and reception. Okay. So transmitting is that you are placing the data on the bus and somebody else is going to read it, and the receiver is just the opposite. It's basically the device which is reading the data from the bus. Right? And remember that only one device that is addressed here, whoever is the address from the master is going to read the data. Right? It might not make sense for the other devices to do that. So let us understand the protocol. So there are 2 things here, which is pretty which pretty much determines the data transmission. There is something called start and stop. So these are the 2 conditions that will be initiated by the master device, the microcontroller in this case, let's say, who is controlling the transmission to the sensor devices or the slave devices. So the transmission is initiated when the master issues a start condition on the bus, and is terminated when the master issues a stop condition. And in between these 2 states, the data transmission will take place. Okay, so a more common example is, let us assume, is data being transmitted from the microcontroller being configured as the master and the sensors being configured as slaves. Whereas you can do other way around, you can have multiple masters and so on, but we are not going into those kind of variations, although the protocol allows those kind of things. Okay, so the start condition is kind of predefined. So when the clock is high, if the SDA, the data line, is pulled low, that basically initiates the start condition. Okay, and this is done in hardware. You can instruct the hardware to initiate a start condition and it will do the same thing. And similarly for the stop condition, it is the clock line high, and at the time when the clock line high, the SDA pin is pulled from low to high, which basically creates the stop condition. Okay, which means that the data transmission will stop at this point of time. And in between that, there will be data transmission, which is in blocks of 9-bit frames. And this, within this 9-bit frames, what you can do is we can send the 7-bit address, or the slave address, it is called SLA. And then there is one more bit. So this is one more bit. So this is 7 bits for the address, 1 bit for telling whether you want to read data from the slave or you want to write data to the slave. And after that, right, so this is SLA R or W that takes place for the first 8 bits, and the last bit is up to the slave, because given the address, because there will be many slaves would be listening, and it is going to do a comparison of its own address and the address being sent on the SDA bus, right? Based on that, the relevant slave will respond by pulling down the acknowledgement bit, right? So in the last clock, the 9th part of the clock, 9th clock pulse, it is going to send the acknowledgement, right? And then after that, the data communication can begin. So this is how the negotiation in between the master and the slave is established, that who is going to respond, that is determined by that 7-bit address that the master has requested. And it might happen that no sensor responded because there is no sensor or a slave device that has this address, right? In that case, there will be nobody sending this acknowledgement bit at that particular clock. So the master is going to definitely understand that there is no such device, and it will be treated something as a negative acknowledgement or NACK, right? And then the further communication will not make sense from the master side to that given address. And this is the continuous data transfer. This is where you start with the address. So this is the what we called SLA plus the read or write, followed by the acknowledgement, and then there will be a train of data that can be sent or received from the master depending whether you want to read or write. So there are variations to this. For example, it might look as data to the bus, right? Because for the bus, all that matters is what is the address of the slave device, and anything that is sent other than address is like data, right? But for the sensor, you might need further configurations, right? For example, after you complete the addressing, right, and the acknowledgement bit is said, maybe depending on the sensor, how it needs to be configured, it might need some register address, right? You are asking some data, let's say, to be read out of the sensor, but the sensor has many kinds of data to give you, right? So it does not make sense to tell the sensor that I want to read out data. You need to be more specific and maybe send some kind of a register address, right? That is how the libraries will be implemented. So they, after this let's say handshaking thing takes place, you need to send out some more relevant information for the sensor in order for it to understand that what kind of data you want to write. Let's say you want to even write data. So for writing data, you need to tell it where you want to write data, because it will also have a tiny fragment of memory, right? Where data will be stored or some kind of configuration settings will be stored. So it is often the practice that you also send some kind of register address, or I would say some kind of control information, right? Control information. And once that control information goes to the sensor, it knows what exactly to do. Okay. And often it is the case, let's say there are like it's, let's say, something like an EEPROM, right, where you have successive memory locations and you don't want to send every data bit and then address to write that, where to write that data, right? Often it is just, there is a automatically programmed to pre-increment or post or decrement it, right? What you can do is, let's say in this sensor you have n memory locations, and what you do is that you give the first address and then keep on putting data on the data bus. What that device will do is that it will write the data in that address and then keep on incrementing the address by 1 every time a new data byte arrives, right? So there can be miscellaneous configurations that you can do. Okay, so this all depends on that particular sensor. That has nothing to do with the I2C bus or this protocol. So after your SLA, RW, and the ACK is sent, it is up to you how you want to negotiate the data in between the microcontroller and the sensor. Okay, so that is the application level logic. So this is how the I2C subsystem looks like. So again, as I told you a few minutes back, it will again have a set of registers, right? So this will be controlled by a set of registers, and in this case there are 5 important registers that I am going to show you. So the first one, we have a very sophisticated bitrate management system. What will be the speed of the data path to a particular sensor that we can actually manage, right? So the bitrate register is going to do that, which is called TWBR. And by the way, we use this terminology called TW, which is mentioned by AVR as the two-wire interface, right? So there are some slight differences in between the two-wire interface and the I2C actual protocol or the actual standard. But in most of the cases where we try to talk to a certain sensor device for our purposes, there won't be much differences. But there are some things called clock stretching and so on that I won't specifically talk about in this class, right? But what this AVR guys mention about this I2C system is they call it the TWI interface or the two-wire interface, and this two-wire name comes from these two pins SD and SCL, right? Whereas in case of the SPI bus, we were having 3 or 4 wires, right? And if you have more devices, you might have more chip select pins, right? So you need MOSI, MISO, and the clock. So those are the 3 pins. And as you increase the number of slave devices, you might need more bits to address them, right? Even if you use something like a multiplexer to address or select a certain particular slave device. Whereas in this case, it will be only 2, and there is a robust addressing scheme. We are going to directly read the address and or write the address to the address bus and request a particular slave to respond, right? So they will check from the data that that address is matching their own address, and based on that they will reply. Okay, so you can scale it up to 128, like 128 devices. So this is the bit rate. Next is the address register. So this is used for in the slave devices because they are going to look at the SDA pin, the data bus, and going to look at whether the requested address is matching theirs, right? So there is an address comparator, and the address register will have the address that is there in the SDA bus, and it is going to compare that, and if it matches, it is going to respond, otherwise not. So this will only be used if you are trying to program a slave device. Most of the sensors are configured as slave devices, so there is already an address it has, and it is going to do all these things in hardware, right? In your master or the microcontroller, you don't need to do this unless and until you are configuring that itself as a slave device. And then you have, as always, there are some status and control registers where you can notice all sorts of let's say interrupts, right? Let's say whenever you are done with the transmission or you are done with the reception, you want to configure the prescalers and so on, right? For that, you will always need the status and control registers. Okay, and apart from that, you also have the data register where you actually want to load the data to send it out, or you want to read the data from there. Okay, so we will discuss a little bit about what are the bits that you need to have a minimal working system. Of course, there are advanced functionalities or more time critical things where you want some more advanced features inside this I2C programming thing. But for that, it will first let's go through the basic things, and then we'll if we have time later, we'll try to see some other non-trivial or uncommon things which can what can be achieved using this thing, right? So let us first look at the very basics. So these are the 5 registers. Earlier, in case of the SPI, we just had 3, and we will see how to program these and what do they mean and so on. So this is how the this is the flow or the state diagram how the I2C data communication takes place, and it starts with initialization, right? Earlier also we saw that you have to enable that particular part of the peripheral device. So here there are 3 specific things that we have to look at. One is the TWEN, which is going to enable that particular hardware piece, and we might have to use this TWEN bit many times where you want to even do a data communication and so on. And then there are 2 other things which are also important, is come up with a bit rate value, we are going to see how the bitrate value is actually calculated. For that, you need two things. One is the TWBR register, and then the value of the prescaler, so which is there in the status register. In the status register, if you see the last 2 bits, that is known as the TWPS bits. So this combined with this 8 bits actually determines your data rate. Okay. So it's a little bit sophisticated than a simple prescaler divide that we used to see earlier in some of the peripherals that we have already seen. But in this case, you have a little bit more options to control the bit rate. And after this initialization has taken place, the next thing that you need to do is transmit the start. Right. So if you remember, the master controls the start and the end points in the transmission, and within that the data communication takes place. So the master has to transmit the start, and this is done by enabling the TWSTA pin, STA bit inside the control register. So if you see here, in every conversation we are trying to do we are trying to transmit some bits, or even transmit data bits or receive data bits, we always have to use the TWEN, which is here, and the TWINT, which is here. So these are the bits which are related to raising interrupts and so on. And then apart from that, we are trying to raise the start condition. So this is going to send the start bit out. So if you just enable that particular bit, the hardware is instructed to send the start bit. And how do you know that the start bit has been sent? We typically do a polling. That also we have seen in case of SPI, or when we were trying to send the serial data, receive the serial data from the keyboard. If you remember, we are trying to poll the clock, right? Whether it is moving, whether it was in the true state or the low state or the high state. Right? In this case, also we are trying to poll for the TWINT bit to know whether the start thing has completed. The start is transmitted to the data bus, or data as well as the clock. Right? Both the pins are important here. So whenever that has finished, you can know by the change in the TWINT flag. Then we have to do the transmit of the received data. For that, the first thing that you need to send is the SLA, or the slave address, along with your request to read or write. Okay, so this is the first thing that you need to do in order to select a given slave. Okay, and for that you need to write your data in the TWDR register. Note that in case you want to send the first in the beginning of the communication, you want to write the address of that particular device, right? So in that case, in the TWDR register, you are going to write the address. Okay, and then these things will be there, because for the TWINT and so on, this will be used to know whether the data communication has ended successfully. Okay, so given that you are writing, so you will send the address out, and after that you are going to wait for the successful reception or successful transmission from the master, and then you will keep on communication, right? Given that how much time you want to keep on communicating, and because you have to send the data out to the sensor, and then the sensor is going to send some data to you, and based on the predetermined protocol that the sensor follows, right, in the application for the logic, the master needs to talk to that sensor in that particular way, right? So from this communication, although it uses the I2C bus, but what data you are basically going to receive from the sensor, or how you are going to instruct the sensor to send you data, that completely depends on the sensor's hardware. And after the master is done with sending the data out, complete data out, or reading till however it requires to read, after that it is going to send the stop condition. Okay, once the stop condition is done, is basically setting the TWSTO flag, which is there in the control register also. So once this is sent out, this is going to indicate that your data communication has completed, and this entire thing will be deinitialized. So you are done with the data communication with the sensor. Okay, so these are the basically the 4 steps, and the transmission could be either a transmission or a reception based on whatever has been agreed upon. So let's look at some of these code fragments. It's not very difficult, and this basically forms the driver for your I2C interface, and you will see that high level libraries are already present which does this kind of jobs for you. So this is for you to understand if you want to go low level in actually trying to understand that how the sensor is communicating to the microcontroller. Because if you just look at the very top level APIs, it's very difficult to figure out how the bare bones thing works, right? And at the very low level, because in that case you will be overwhelmed by the number of registers they have and very sophisticated schemes that the sensors implement, right? So it's better to see some very simple example and then have a general understanding, so that you can send even a simple byte to a slave device, and then we can build on top of that, right? That's how all these libraries are written. Okay, then it's kind of easy for you to dissect a given library and see how the code flow goes in actually querying the sensor registers. So for initialization, as I told you, that we have a substantial freedom, right, in controlling the clock frequency. So how this is done is CPU clock frequency divided by 16 plus 2 into the value inside the TWBR. So the bitrate register is this TWBR multiplied by the prescaler value. Okay, so the prescaler value will be the bits that the last 2 bits in your status register. These are the prescaler bits, and then so there would be a lookup table given that you have like 0 0 or 0 1 1 0 or 1 1. What is the corresponding value you can get? And apart from that, you will also have a value which is the byte that is contained by the TWBR register. Okay, so that you can set given, so that's why I put a question mark. So you can put that particular value whatever you wish. Same for the prescaler bits. So this will determine your clock frequency, and then you want to enable the TW module, like two-way interface module, and for that you have to write you have to enable that particular TWEN bit, which is basically in the control register. So the TWCR, within the TWCR you are going to write the value of 1 here, right, which is, and the rest could be 0 depending on our application, right, whatever we want to do at this point in time. So we have written a value of 4. And next what we want to do is that we want to do the transmission of the start condition, and we need to pull the TWINT register till we know that the start condition has finished, right? It has successfully sent out the start condition to the bus. So how is it done? It's again going to manipulate some of the bits inside the control register itself, which includes specifically the TWINT bit, the TWSTA, which is the start bit, which is basically responsible for sending out the start condition, and the enable thing, right, the TWEN. These are the 3 things that are normally activated if you want to do the send out the start condition to the bus. And after it is sent, we have to wait for some amount of time till that thing has finished, till the start condition has finished, so that next we can start communicating the data. Okay, so this is again a polling as a busy wait, where we try to look at the value of the TWINT bit in the TWCR or the control register. Right? Once this is done, we can be sure that this I2C start is the function that could be called from the main function to finish sending out the start bit or the initiating the start condition. After that, we want to have the reception or the transmission of data. So we can do two things. Either what we can do is that we can either write some data, and in this case, if you want to send the address first, right, you definitely want to write the data, and that data will have initially a combination of the address as well as whether you want to read or write. So the data, the value inside data should encapsulate those particular things, keeping the protocol in mind. Okay, and then these are regular things that we want to again enable the TWINT and TW enable, and then do a busy wait till that particular data communication has completed. Okay, so this is about the write, and similarly for read also, we want to if the data is being sent from the remote device or the slave device, we just want to wait till the time the data has been received, and then we want to read the value of the data register. So the data register will contain the data that has been received, and now we can process the data or like store the data in the memory and so on. Okay, so this is how at the low level the data communication can take place, and whether like what is the series of operations that you need. So this is basically just communicating one byte, right? So now your sensor might expect multiple bytes. Let's say you have a 16-bit register, right? Or the data that you are reading from the register is 16 bits long. So in that case, you want to read it twice, right? So those kind of negotiations or applications has to be predetermined, and you have to know the application that you are developing in the microcontroller. You need to know how the particular sensor is going to respond. If it is just a byte, that is not a problem. You can just simply read a byte like this. The I2C interface is going to allow you to read 1 byte of information like this, and then you have to read another byte. So only if you get these 2 bytes together, then only your data is going to make sense. So you need to read the TWR register maybe twice, and then that's how you want to develop your application logic on top of this. Okay, this just gives you a basic functionality, how to read 1 byte or how to write 1 byte of information. And then we, very similar to the start, you can also send the stop signal out, or the stop condition out is just by putting 1 in the stop bit in the control register. Okay. So we know how to send a start condition. First initialize with the bit rate register prescaler, and then enable the TWI peripheral, then send a start condition, receive or transmit the data, and then send a stop condition. That is how the data communication using the I2C interface takes place. Okay, and any sort of sensor you buy these days, right, they will always have an I2C interface, most of the cases, and they might even have additionally SPI bus also, right? And sometimes they might have just the SPI bus, right? It depends on what kind of data rate that particular device is going to give you. Normally, I2C device does not give you a very high data rate, right? It could be at most 1 or a couple of megabits per second, right? Not more than that. So as in the case of SPI library, also we have this Arduino library support. So whatever I have shown you, these are all sort of implemented using this top level functions, right? The where.h is the library header here that you can use in your application code in order to program or write a library for a certain sensor. Okay, so these are going to give you the very low level functionalities. For example, you can write a byte, or you can try to read a byte, you can set the clock, right? So these are all going to, if you look at the implementation of this particular functions or the APIs in the where library, you can see whatever they have done will be very similar to whatever we have just studied, right? So they will have much more corner cases, much more robust code, right, to handle failures. But they will have some kind of a version of this, right? They will handle timeouts and so on, right? This might happen that your device never responds, and that means that your the program or your application code is going to run into an infinite loop. For that, you might actually have some kind of a countdown timer, right? Even if it does not respond in let's say this much microseconds, I am going to kill that particular request and then go to something else. Okay. So if you have time, if you can look at one or two of these implementations, how the where.h is actually taking help of the TWI interface, and then the TWI interface is going to have the implementation. So where.h is something like a wrapper which is for the I2C interface, which is going to have some of the extra functionalities that the native TWI interface might not have. So this is just a wrapper, right? It's on top, and this is going to be implemented. Most of it is taking the help of the TWI interface, right? This is the API is being provided by the TWI. And then if you look at the functions that are inside this, right, you can actually see the actual implementation here. So these are, if you install this Arduino, all these libraries are already installed in your system. So you can just go and read the source code. Just reading the source code will also, like if you try to navigate through the source code, that will give you pretty much a clear idea about the flow of logic. So this is the way you want to program using the where library as an Arduino Sketch. So you need to do this initially. You want to do the where.begin, which is going to do all the initialization stuff, right? And then you can always pass on configurations here, right? So you can do a pre-configuration based on what kind of data rate you want, or if you want to set the clock and so on. As you already have seen that those features are available. And then initially you have to do some kind of a sensor setup, let us call it, right? So every time either you can do it on the setup if it is only one time, or if it is like every chunk in time you want to change the setup. In that case, you can keep this configuration inside the loop also, right? So you want to request by giving the address. Let's say this is the address of your sensor. You want to write something to the sensor so that you know that where to receive data from. So this is an example where I took from the support library standard example. This was basically an ultrasonic sensor, right? It's an ultrasound sensor. This is going to transmit certain data, an echo, like a sound pulse, and then after it gets reflected in the reflector, this is going to come back as an echo. So this is known as the echo. And then I can try to determine the distance from the transmitter to the obstacle, right? So this distance can be calculated. So this is all the sensor does, and that is not important here. What we try to do is we pass on the address of the particular sensor so that it is discovered in the I2C bus, and then we try to do some register configurations, then we end the transmission. So this is basically, I have mentioned sensor setup, setting up the registers, putting some initial configuration, and once this is done, we keep on reading data out of the sensor. Okay. So as you are seeing here in this case, let's say we are reading 16 bits. So reading is equal to where.read we are doing, and then we are basically reading 2 bytes. Right? We are reading the first byte and then shifting it to the shifting it by 8 bits, and then we are reading the least significant byte. Right? And again, these definitions also should come from the device manufacturer, right? Whether they want to send the most significant byte first or the least significant byte first, right? So that has nothing to do with our code here, right? This is an example to show you how the where library works, right? So typically the application flow will be like this. If you want to discover the or kind of navigate through the code yourself, you can try to take a look at this. So you have the sensor library APIs. Any sensor you can pick up, right? Like a temperature sensor, let's say, that uses, let's say, SPI bus, right? You can download any library like this. Even if you don't have the sensor yourself, right? You can try to see how they are implementing. So you'll have something called a read data or read temperature, and then try to follow what exactly happens before it, how it exactly goes to executing a call from the register. Okay, and they will have this set of APIs, and those APIs will be using the where.h library, right? Those are, I would call, the Arduino APIs. Right? Read data or write data, this kind of libraries, that like library functions that I showed you right now. And they will be, this will be implemented, the where.h basically will be implemented on the, we will have a separate wrapper called I2C and then the TWI. There are like these two things there. Okay, and if you look at the implementation of the TWI.cc, the C++ file, you can see all the registers that are being read here. Okay, so at least for one function, I would ask you to go through this flow so that you actually have an end-to-end understanding of how the data is actually read from the bare hardware registers, right? And how and if you happen to have the sensor, that will be better. Then you can even tweak the code and do some kind of small debugging on your end. Right? So that will help you in order to understand the protocol better. So there is one more thing that I just want to mention, is about the blocking or the halt of the CPU whenever you are basically doing this busy wait, right? So we have encountered this multiple number of times, and I'm not going to go into much more details about how to mitigate this thing, but there are certain active industry white papers, right, that I will ask you to refer to, where you can see that how people are thinking that this kind of bottlenecks, right, could be mitigated in software. So if you see common I2C implementations, right, using third-party libraries, they will implement the start and the stop bit sending or the data read and write. They will use this polling approach where this is going to continuously look at the TWINT bit, right, to know whether a byte is transmitted or received successfully. And how this is going to impact your system. So if you look at this entire timeline, when you send the SLA plus RW request, and after that, whenever you send a request for sending a data out, and this time you need to wait, and you have requested to send the data out, and after this amount of time only the interrupt will be cleared, and then only you can go and fetch the next data and then write that data to the memory and so on. But this amount of time you are doing a busy wait, right, which could be spanning several hundreds of microseconds, right, because this is the time that that the bus will take to transport the entire frame, right? How many bits you have, right? In this case, you will have the start and the stop, and then within that, let's say it's a byte, right? You have to wait that amount of time. Okay, so the CPU is not doing, as you are understanding, anything useful. So I will point you to one algorithm that you can see, which is based on interrupts, right? Typically, the solution for this kind of problem is using interrupts, and the implementation of the particular kind of algorithm that I am talking about is available also. So it's like it will take too much of time for me to go through that and make you understand. But if you happen to be comfortable in C programming, right, that will not be a much of a problem for you. It's very well documented, and I will like you to look at that particular kind of thing, right? That is going to also add to your programming skills, right? If you happen to implement it, like you can just use that implementation and try to run that on your system. Okay, so there is this non-blocking I2C version, which you will not find in commonly available libraries that you see around, right? They don't support this non-blocking feature. So the aim is the non-blocking communication, where the CPU will not wait until each byte is transferred. The algorithm allows for the application to continue execution, right? So often what happens is whenever the data comes in, you want to do some kind of a running average, or you want to filter noise out of the data. So you want to basically do some kind of statistical processing once the data comes in, right? And you happen to have a queue, and you keep on updating the queue, right? And then update different variables, right? Suppose you want to keep track of let's say the distribution, standard deviation, things like that, and those kind of things will has to be immediately calculated after the byte arrives, right? And you don't want to do some kind of busy wait for that particular time, right? Because it is going to waste a lot of CPU cycles doing nothing, right? So that is the reason I wanted to touch upon this particular thing. This is very essential for this IoT like devices, right? Where you want to maximize the efficiency of your microprocessor. Okay. So after the byte is transferred and the ACK is received, the I2C module triggers the interrupt, and somehow we are trying to catch that in the state machine. The state machine is nothing but you have the start condition, data transmission condition, stop condition, and then basically an initiation of the next byte takes place. So the interrupt service routine has to be implemented whenever the acknowledgement for the transmitted byte arrives. So that's the implementation these people have, right? One of the commonly available implementation is you can look at the NXP's code. They have this white paper. I'm going to share this with you, where they talk about an interrupt that the microcontroller is going to generate on the acknowledgement when the acknowledgement arrives, and then service the interrupt service routine. Okay, they are going to implement the interrupt service routine, and then they have implemented some kind of a state machine where they declare the start condition. After that, the bus becomes busy. If the acknowledgement does not arrive for a sufficient amount of time, they will declare a fault, and so on. So it's a little bit long in terms of the logic is in terms of the algorithm. I would definitely recommend you to look at it. Maybe after your exam is over. I'm not going to have all these things now in the exam, but for your own knowledge, you can try to look at this small variation, right? In even in SPI or the serial communication, all the examples that I've shown you in the driver were using blocking calls, right? So the concept is still the same. If you want to basically have a non-blocking version, you want to use an interrupt, and then that's how the trick is, right? How are you going to best use the interrupt, right? With the available resources. You can even use a timer. Let's say you know that this data communication takes this much amount of time maximum. So after that, a timer might expire, and then that might raise an interrupt, and you basically want to come back to the code and service that particular interrupt. So those kind of variations are also possible. So there are multiple variations to this, how it is implemented. This is one example. I'm going to share this with you, and you can take a look, and if you have any questions, we can discuss. Okay, so I'll try to conclude this our whatever we have covered in microcontrollers and sensing. So I'm basically, there are certain things that are still missing. We are going to cover that later. So we started with basics of instruction execution, the processing unit. We try to look at what is the ALU, how does it execute instruction fetch, instruction decoding, and so on. After that, we looked at the memory from the perspective of a microcontroller, where code is stored, the SRAM, the bootloader is stored in the flash, and so where the binary that you are actually loading, the application binary is stored in the flash, the registers, the CPU registers, the input-output registers, how they can be programmed in order to control the different ports, the general purpose input-output pins. Those were covered, right? So we had a good idea about handling the memory, right? Particularly in our case, we will require the registers and the input-output, because we have to talk to a lot of different peripherals, and for that this becomes more and more important, right? And what we have been historically doing for the last few classes is just looking at lots of different registers and how they can be configured in order to configure a certain peripheral, because this is your medium to talk to the hardware. So this is like the software hardware interface. Okay, so like all this, the registers as well as I would say the input output registers, right? This is your the software's gateway to the hardware. So that's why this is so important. And we have seen fragments of code, right? Not exhaustive, but I have given you enough pointers to help you start with Arduino programming, and you can write a C program, right? All the functions that I was showing you, so that all these peripherals could be programmed, right? At some decent level. Okay, we have not seen in any extremely advanced application, but as a beginner, right, you would be able to do some basic programming. And there were these peripherals. Some of them we have covered, and some of them are not yet covered. We will see what we can do, right, as we proceed in the course. So later we might require signal generation, right? We want to create some kind of a pulse, right, for doing some kind of specific sensing work, right? In that time, I will probably try to cover timers, right? How to program timers, right? But till now we have covered interrupts in some details. We have covered ADC, how to program ADC, and we have in the digital part we have looked at serial data transfer. In between in the keyboard example, we have covered some details. And apart from that, we have also looked at how to interface digital sensors using the I2C and the SPI bus. Right? So you for now you should have some comfort in this part, right, where you can have the technology ready for communicating to a sensor. Right? You have some idea about these registers. You know how to program them, and you have some knowledge about the different interfaces that could be used for interfacing analog sensors or digital sensors. Okay, so some of this, the yellow, whatever is highlighted in yellow, we can do these things later as time permits, or as a part of the different sensing case studies that we are going to do when we try to implement them. And in sensing, we have looked at in details. We have looked at how an event is detected, what are the statistical fundamentals behind that, and some details regarding quantization in connection to the ADCs. We have looked at effective number of bits, like in order to achieve a certain SNR in the ADC. So the frequency part we have not yet looked at. So whenever we try to look at periodic signals, or particularly when we try to analyze certain periodic signals while we delve more into the sensing applications, in that time I'll try to look at, maybe I'll give you a tutorial on Fourier transforms like FFT and spectrograms and so on, right? Right now we will stop here, and after your exam is over, we can focus our attention to different sensing applications. And as a part of that implementation, we are again going to come back to this concept that we have already studied, right? Let's say you want to read an analog value, but the focus will more be on the algorithm part now, right? Once you read the analog value, suppose you want to do some kind of a peak detection, right? Let's say in the step counting example, if you remember, all we were doing was to read an analog value, right? So, and then after that, once you plot the data, you saw something like this. And maybe you want to look at how many peaks are present, right? How many peaks per unit time. So those are more algorithmic concepts, right? You know by now that how the data is read, how the hardware pipeline works, right? Now it will be a little bit on the software or the algorithmic part. Okay, and trying to understand also the different modalities. We have not seen much about the sensors, right? Suppose you want to achieve a certain application, like certain application in mind you have, what are the right sensors for your choice? Right? If you want to do a gesture tracking or gesture recognition, let's say, right? What are the sensors that are available? What is the accuracy they might have? What is the computational complexity in order to process that data, or in order to implement a certain algorithm? Those kind of things we will see. Right? So this big picture you should have in mind. If you miss certain things, you should go and read it up. Right? I might not have exhaustively covered everything that you see in the picture, but most of it is covered, and you have a fairly good amount of idea about how to do these implementations as well, right? Apart from just the theoretical part, right, the computer architecture details, you should have some programming idea also about how to access these different things. Okay, so we will wrap up today's class here.